Good evening, AP Chem. This is your Unit 8 review. So without further ado, let's get right into it. Sorry, I was muted for 9 seconds, and I didn't realize it. So let's start with 8.1, aka the basics of acid-base chemistry. So 8.1 wants you to pick a definition that AP wants you to pick. Now, there are three main definitions that you want to use, right? You have Arrhenius, I'll abbreviate to ARR, Bronsted-Lowry, BL, and Lewis. You might remember from your Lewis dot diagrams. Now, Arrhenius, who was a big kinetics guy, said that acids produce hydronium ions or protons, and bases produce hydroxides or, well, hydroxides. However, this really limited the base definition to strong bases, or those that contain hydroxide, which wasn't really that inclusive of other bases like ammonia. Now, Bronsted-Lowry, that definition says acids produce hydronium, or protons, and bases accept hydronium or protons. Now, the reason why I'm saying hydronium or protons is because these two notations, AP prefers you to use hydronium. However, protons are also acceptable by AP standards. Let's get back to the definition debate. Lewis said that acids accept lone base pairs, lone electron pairs, right? And bases donate lone pairs. Now, this can get really useful when you're talking about more niche acids and bases, like boron, that has a lot of interesting acid-base chemistry there. By the Lewis definition. By the Bronsted-Lowry or the Arrhenius definition, it really doesn't. So really, AP wants you to use the Bronsted-Lowry definition of acids and bases. Alright? So now let's move on to 8.2, which is strong acids and bases, the pH and pOH of strong acids and bases. So we can say that a strong acid, yes, I abbreviate them SA, to be anything which dissociates 100%. Into hydronium ions and their conjugate base, which I will label B-. Alright? Strong bases, on the other hand, is anything similar to the strong acid definition, is anything which accepts protons, or hydronium ions, 100% of the time. Alright, so that, which would create HB plus and OH minus, usually. So a great example of both of these is the strong acid and base list that you probably have been taught. The strong acids I'll give you 3 seconds to name all of them and shout them at your screen while I just stare at the screen on my end. are hydrochloric acid, hydrobromic acid, hydroiodic acid, perchloric acid, HClO4, nitric acid, HNO3, and sulfuric acid, H2SO4. The strong bases are usually anything that is within group 1 or 2 paired with hydroxide. So that includes lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, and group 2, which would include beryllium hydroxide, magnesium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. I don't want to write them out right now because I don't have room on my little paint file. So why are we calculating pH and POH when we're just covering definitions at this point? It's because this is actually a very useful skill once you actually get the hang of it. So, again, by a Bronsted-Lowry definition, an acid is anything that will produce hydronium ions. And so, we can measure the acidity of a solution by measuring its hydronium concentration. Now, you might have already heard of the scale that we use to do this on, and it is called the pH scale, which goes from 0 to 14. Usually. I say usually because there are some substances that can go to -1 and some substances that can go to 15, but that's really not relevant to AP. So, pH, if you see a P in front of anything, a lowercase p like the one in pH, that means that we take the negative log. So, if you have a hydronium concentration of 1 times 10 to the negative 7th molar, to get the pH, you would take the negative log of 1 times 10 to the negative 7th. Which, if you take the log, that's negative 7, negative 1 times negative 7 is 7. And, we know one significant figure. The reason why the significant figures are counted after the decimal point is really confusing. So just trust me on this one. We can start counting significant figures after the decimal point, not before the decimal point for pHs and POHs. Now, what you might not have heard of is the POH scale, which is the same thing as the pH scale, except for basicity. So we have POH. And again, like the pH scale, this is a scale from 0 to 14. There are some substances that can go into the negatives and some substances that can go above 14, but those are regarded as really non-relevant. You can dig into more research if you want, but I'm covering what AP wants to cover. So if you have a solution that is concentrated in hydroxide at 1 times 10 to the negative 7th molar, to get the POH, you take the negative log of OH minus, which again is the negative log of 1 times 10 to the negative 7th molar. The log of 1 times 10 to the negative 7th is negative 7. You multiply that by negative 1 and you get 7.0. So now we can go up to 8.3, which is which is weak acids, weak bases. Weak acids and weak bases, as you could probably tell, don't dissociate 100% of the way into hydronium or hydroxide and their conjugate acids and bases. They're really they can dissociate some of the way, but they don't dissociate all of the way, which is why they're called weak instead of strong acids. So, what weak acids really do, sorry, I forgot to change the counter up here. What weak acids really do is they're actually useful for chemistry because they don't necessarily change the solution one way or the other too quickly. You can actually use this to do buffers, titrations. You can have this as your titrant and your or your analyte, which is really interesting. So, so let's say that we have so again, as part of weak acids, they have, as you may recall from Unit 7, anything that doesn't go all the way to completion usually has an equilibrium point, and weak acids are no exception. If we ever, and this is a general case, right? HA. If we go H plus A minus, right? Because charge balance, this arrow isn't actually a one-way arrow, it's a two-way arrow because it is an equilibrium. And this has the equilibrium dissociation constant called Ka for acid dissociation constant. And it's the same thing for bases too. If we have bases here and we add water, we can say that this dissociates into Hb plus and hydroxide ions, and this is called Kb. So now let's do an example. Say I have an acid, Ha, which is weak, that has a pH of 4. Alright? So now what is the hydronium concentration? Not the hydronium, the Ka of the acid. Sorry. Pause the video or just allow me to say it through your screens. But please, work it out once I'm done so that you know what to do. So what you want to do is set up your Rice tables, reaction, initial, constant change, equilibrium. You have HA with equilibrium of H plus and A minus. So your initial concentration, we'll say is 1 molar, 0, 0, minus x plus x plus x, 1 minus x, x, x. Right? And so now at equilibrium, you have that H plus is equal to 10 to the negative 4, because that's the inverse of negative log, is taking the negative value to 10. So you have x equals 1 times 10 to the negative 4, and A minus is equal to 1 times 10 to the negative 4, H plus is equal to 1 times 10 to the negative 4, and HA is equal to 1 minus 1 times 10 to the negative 4. So Ka, if you will recall, is H plus times A minus over HA. And this is equal to 1 times 10 to the negative 4 times 1 times 10 to the negative 4 over 1 minus 1 times 10 to the negative 4. Alright? And that is equal to, let me get my calculator out, 1e negative 4, square it, divided by 1 minus 1e negative 4. And we get 1.00 times 10 to the negative 8. Which, the more observant of you may have noticed that it doesn't really matter whether or not we used 1 or 1 minus 1 times 10 to the negative 4, because the outcome didn't round to enough significant digits to actually count towards our final Ka value. This is what is known as approximation, and is actually really useful for some of the more difficult weak acids that you may have to work with. For instance, you might work with acetic acid, CH3COOH, which dissociates into acetate and hydronium. If you have a really if you have a really big concentration as your initial concentration of your acid, you can really just ignore the contributions made to diminish that concentration by acid and acetate, because the initial concentration is so big. This is called, again, approximation. I know that the pKa is equal to 4.74, and the Ka is 1.8 times 10 to the negative fifth. If I were to, say, have the initial concentration be 1, and I have these both be 0, plus x, minus x, minus x, right? And, well, minus x plus x, sorry. And you have x, 1 minus x. This can get really tiring of just solving quadratic equations, especially to something with such a small value like 1.8 times 10 to the negative fifth. So what you can do is you can approximate it to be 1 minus x is approximately equal to 1. Now this is okay so long as your approximation for x ends up being less than 5% of your original concentration, so that we know that you're not introducing too much error. In this case, I know that my concentration of acetate and acid are not going to be greater than 5% or 0.05 of 1, because the Ka value is so small. Now, let's move on to 8.4, acid-base reactions, and Kw. So now, a lot of you might have heard that pure water has a pH. This is called autoionization at 25 degrees Celsius, and yes, I am specifying that for a very good reason. At 25 degrees Celsius, the pH of water is equal to 7, and this is known as autoionization. What water does is it reacts with itself to form hydronium and hydroxide. And at 25 degrees Celsius, each of these two ions are exactly 1 times 10 to the negative 7th molar in concentration. At a higher temperature, the concentrations may get a little bit skewed off. Luckily, AP only expects you to know at 25 degrees Celsius. Any higher or lower, they'll usually give you the concentrations. So then we can introduce what is called the conjugate seesaw. Well, not conjugate seesaw. So Kw is always going to be equal to 1 times 10 to the negative 14th. And this is the equilibrium constant for the autoionization of water. So acids and bases will usually multiply to give this number. pH of water, again at 25 degrees Celsius, is going to be equal to 7. That means that H plus times OH minus is equal to 1 times 10 to the negative 7th times 1 times 10 to the negative 7th, which would be 1 times 10 to the negative 14th. So, we can do the exact same thing for our Ka, Kb values. If you know the Ka value of a weak acid, you know the Kb value of its conjugate base. So if you have KaHa, then you have Kba minus. And this comes from basically just any sort of arrangement of it, right? Ha will produce hydronium ions, A minus will produce hydroxide ions, and again, Kw will be those two multiplied together, which is always going to be 1 times 10 to the negative 14th. So Ka, Kb is equal to Kw. So let's do an example, shall we? Again, let's use acetic acid, CH3COOH, and CH3COO minus. So this is acetic acid and this is acetate. Now I know that the Ka of acetic acid is 1.8 times 10 to the negative fifth. Now, to find Kb of acetate, I can do a very similar process to what I just did. However, it's more of a common application. So I know that Kw is going to be equal to 1 times 10 to the negative 14th. And Ka is equal to 1.8 times 10 to the negative 5th. And Kb is always going to be equal to Kw, or 1 times 10 to the negative 14th. Which means I can do some algebra and solve for Kb, which is 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5, which is 5.56 times 10 to the negative 10th. Not 5th, 10th. And so this is the very basic principle behind what I think is known as the conjugated seesaw. The stronger your acid is, the weaker your base is, to the point of where you get the strong acids have very weak conjugate bases. So now we can move on to titrations. So titrations work in a very unique way, where you're trying to find usually trying to find the concentration of an unknown solution. So how they work is, and you've probably already done this, is you take what's known as a burette, and you pump the solution in the burette into an Erlenmeyer flask. I am sorry, my drawing skills are not very good. Kind of like this. So then you know the concentration of the solution in the burette, and you don't know the concentration of the solution in the Erlenmeyer flask. So what you can do is you can sort of drip down the known solution into the unknown solution, such that you can tell exactly when the unknown solution is completely used up. And this is known as a titration. So there are really 4 different types of titrations: strong acid, strong base; strong acid, weak base; weak acid, strong base; and of course, weak acid, weak base. And now, weak acid, weak base titrations are kind of the oddball of the group, because you really can't use them to determine the concentration of anything. So we can just consider them null for the time being. Now, strong acid, strong bases have a very unique neutralization point at exactly pH, well, whatever the pH of water is at that temperature. Because, and I'm going to draw something called a titration curve here, as you again, drawing skills are not that good. Because as you add your strong acid or strong base, your equivalence point is always going to be exactly equal to whatever the pH is. Now, the equivalence point is the stoichiometric ratio. So say you have 0.1 molar strong acid, 0.2 molar strong base, acid, base. and so your equivalence point for 100 mils of acid would be 50 mils of base. Now, strong acid, weak base titrations are going to be slightly different, because a very good property of weak acids and bases is that they can form what are known as buffers. Now, buffers are defined as being able to resist changes in pH. So, the weak base strong acid titration will start somewhere up here at pH 10, 11, 12, or 13, and it will go something like this. You will have a very large flat area, and then all of a sudden your pH drops, and then you plateau out again. And it is here that is known as the buffer region. Where not really much is happening, so we can just skip to the equivalence point and the end point. Now, I specify that these two are not the same thing for a very good reason. The equivalence point is the stoichiometric ratio. So again, 1.1 molar and 0.2 molar of your acids and bases solution. If you have 0.1 molar and 100 mils of acid, you need 50 mils of 0.2 molar base solution. However, uh, however, the endpoint is when you can actually stop the titration. Because of course you're trying to find the concentration of usually what the weaker substance is, in this case the base. So, so your equivalence point is going to be somewhere lower than 7, usually. And then what you really want to do is find out, okay, which indicator do I want to use such that my endpoint is basically right on that equivalence point. Because again, error is the name of the game. You don't want too much error. So, very common one for strong acid weak bases is, I believe, methyl red or orange. A very common one for weak acid strong bases is called phenolphthalein. Now, I don't memorize the color changes in my head, but what I can tell you is that usually you want the buffer or the indicator which has the most similar pH to your equivalence point. So now we can move on to weak acid strong bases, because very similarly to weak bases strong acids, you have very much the same regions. You have the initial buffer region, the equivalence point, and your base. So you have the buffer region over here. I'll abbreviate to BR. And you have your equivalence point somewhere up here, EP. So now, again, if we're trying to find the concentration of the weak acid, you want some indicator which is about the same color change region as the equivalence point. Usually what you'll use is phenolphthalein for weak acid strong base titrations. And of course, there are loads of other indicators to use when you're considering strong acid, weak base, or weak acid, strong base. So, look at the question and try to pick the best one. Now, there are actually a lot of questions that AP can ask with these titrations. Usually they'll give weak acid, strong base, or weak base, strong acid. An example is if you're titrating 25 mils of acetic acid solution with 0.1 molar sodium hydroxide solution, will the equivalence point be greater or less than 7, or equal to 7? Since we're doing a weak acid strong base titration, the equivalence point will usually be greater than 7. Now, what they can do is tell you you analyze the phenolphthalein point at 25 milliliters sodium hydroxide added. This is where you notice the endpoint and is where you stop the titration. Now, if you've done your indicator work correctly, you will have just also found the equivalence point, which actually is really convenient here, since your acetic acid concentration was exactly the same as your sodium hydroxide concentration, otherwise known as 0.1 molar. So now let's move on to pH and pKa. And really, the whole reason why we would want to study some titrations in the first place. This is 8.7. So pH and pKa are negative logs of H plus and Ka. Now, what these can be is something called a buffer. Now, the pH of a buffer is actually pretty resistant to change, like I said, in 8.5. So, yeah, we can actually model the pH using something called the Henderson-Hasselbalch equation, which we'll get to later. Additionally, we can set the pKa of an indicator to color change whenever we want the indicator to do so. Now, disclaimer, I'm not saying that we can change the chemical properties of a certain indicator. I'm saying that we can choose a certain indicator that has the chemical properties that we need. For example, the indicator that hypothetical HIN has a pKa of 5.2. And now, for the sake of argument, we'll say that it goes from red to purple, right? With some bluish color in between, not black, blue, something like a blue color in between. So now, if the pH is at 6.5, will it show red, blue, or purple? Usually what you'll say is, well, since the pKa is 5.2, that's the color change region. Somewhere within like 5.0 or 5.4 would be when it would show blue. pH 6.5 is way overshooting the endpoint, and you would see purple. So now we can get to buffers. 8.8. Sorry, give me a moment. Sorry guys, I don't know what happened to my computer there. Which we can now cover buffers. 8.8, 8.9, and 8.10. So we'll start with 8.8. Properties of buffers. So properties of buffers, well, first we have to define what a buffer is. It is a mix of weak acid and its conjugate base, or a mix of weak base and its conjugate acid. So we can create a buffer by adding weak base and its conjugate acid together, or weak acid and its conjugate base together, or which is how it's really done in the lab, we can add a weak acid and some strong base to create a buffer, which is why I pointed out the buffer region in the titration curve. So if we draw a weak acid strong base, and a weak base, strong acid here. We can see weak acid, strong base, and weak base, strong acid. Right? So right here, this flat region at the beginning of both of these titrations is called the buffer region. And now we know why. It's because enough base or acid has been added to neutralize enough of the original acid and base such that the mixture resists changes in pH. Very common real life example is in your drainage system, where buffers filter out all of the nasty impurities that you might experience in your day-to-day life. So, we can actually calculate the pHs of these buffers, which we will now get to in 8.9, the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is a way that you can calculate the pH of a buffer given its pKa or Ka and its concentrations of acid and base. So it goes like this: pH equals pKa plus log of your base divided by your acid. So we can use this for all sorts of things. Notably, however, when the concentration of conjugate base or acid or conjugate acid is equal to your acid, then pH is equal to pKa plus log 1. And the more mathematical of you may have noticed that, hey, log 1 is just 0. So pH is really equal to pKa at this point, which is known as the half equivalence point in a titration curve. Because again, if we look at one of these, just gonna draw a quick weak base strong acid titration curve here. If we look at this, if we say that this is the equivalence point, right, at 20 mils, we'll say, then this is the half equivalence point at 10 mils. And it's named that way for a very good reason. Well, you can probably already tell. The volume of acid added, or base added if you're doing the opposite of these titrations, is the exact half of the equivalence point. Now, the half equivalence point has some actually really strange properties, so just keep that in your mind for now. The half equivalence point is exactly when your base equals your acid, which means that pH equals pKa at the half equivalence point. For instance, if we go again to acetic acid, if you have 0.1 molar acetic acid and 0.2 molar sodium hydroxide, it will take, and 100 mils of acetic acid, it will take you 25 mils of sodium hydroxide to reach the half equivalence point where pH equals pKa. Now, I happen to know that acetic acid has pKa of 4.74. And so at the half equivalence point, that is also the pH value since base equals acid and log 1 is 0. Now, you may be wondering, that's cool and all that, but how will AP ask about this? I'm glad you asked. So AP will sometimes ask if I have a certain amount of CH3COOH, and this is just an example acid. They can ask about acetic acid, formic acid, or any weak acid out there in the world, or even just a hypothetical. If I have a certain amount of 0.1 molar CH3COOH, and the same amount of 0.01 molar H3COO minus. What is the pH of this buffer? So now we can plug this into the Henderson-Hasselbalch equation. You have your pH is equal to pKa plus log B over A. And so now we can plug stuff in. pH is, are unknown, so pH is equal to pKa, which is 4.74. AP will usually give this to you, plus log B over A, which is 0.01 over 0.1, which is zero point 0.1. This is going to be -1, so 4.74 minus 1 is equal to 3.74. So now we can get to what is known as buffer capacity. Now, again, buffers have this really good property of resisting pH changes, but only up to a point. And that is when you have the same amount as of your acid as you do, and that is when all your acid or all of your base has been completely neutralized. So if you have hydrofluoric acid and fluoride buffer, the buffer breaking point almost will come when all of the hydrofluoric acid or all of fluoride has been used up. So, so I'm going to set up two buffers, A and B. Say A has 1.0 molar HF and F minus, and B has 0.1 molar HF and F minus. So, of course, due to the pure concentrations, you'll say that A has the higher buffer capacity, and you would be correct. Because buffer capacity depends on the amount of stuff that is in the solution. So, if these were of the same volume, then A would have the larger buffer capacity. So now, let's move all the way back to 8.6, which, if you noticed, was one of the ones that I skipped. Because 8.6 is about molecular structure. So, if you draw all the strong acids, HCl, HBr, HI, HNO3, HClO4, and H2SO4. Uh, you'll notice something. All of these are connected to pretty electronegative elements, and this is no accident. However, I want to stress something about the binary acids, HCl, HBr, and HI. You may be wondering, well, why isn't HF on there? And that's because in binary acids, whilst yes, electronegativity and electron density do count, so does bond enthalpy. If we have HF, yes, fluorine is one of the most electronegative atoms. It will pull electrons towards itself really strongly. However, this bond between hydrogen and fluorine is super short. And you know what that means? It means that hydrogen and fluorine are super strongly bound together, so much so that actually breaking the bond is really unfavorable, and well, just fluorine's electronegativity and electron density isn't going to cut it anymore. So, if we look at all of these, we'll see that hydrogen is almost always electron deficient. And in fact, this is no accident. This is known as, the inductive effect. And the inductive effect is actually something really interesting. It is the fact that if you have, well, in this case, hydrogen connected to a really electronegative element and some other stuff here, right? Then the hydrogen will become super electron deficient. And it really does, yes, it really matters where in this case the oxygen is placed, because if it were placed on, say, a carbon, then yes, the inductive effect would still have an effect, but not nearly as strong as if it were directly connected to the oxygen. uh, Same thing if the oxygen were connected 3 carbons away. This inductive effect is actually now super weak, to the point where we can consider hydrogen non-acidic at all. So this is so additionally, right? If you have a high inductive effect, that usually means you have a pretty good stabilization on your conjugate base. So again, if we have HO and then a side group, we can say R for the rest of the molecule. Then, if we dissociate hydrogen, then oxygen will have a negative formal charge, which it really wants since it's pretty electronegative. So, the same thing applies if you have multiple oxygens, which is why all of these are actually really stable. If you actually draw them out as their ionic forms, being nitrate, perchlorate, and sulfate, you will see that they all have this resonance effect that will actually help stabilize the negative charge across 4 oxygens instead of just 1. Now, the reason that these guys don't need the other stabilizing factors is because that they're stable enough already as negative anions. So let's do an example. Say I have H2SO4, as demonstrated here, and H2SO3. Now, which one of these first protons are actually more acidic? We'll say, for sake of simplicity, that both of their left protons dissociate. And you might be saying H2SO4 because it's a strong acid. However, I want you to keep from generalizing and actually realize the actual chemical effect. So H2SO4, yes, is the strong acid. However, that is because of the resonance effect within its oxygens. So you have sort of like this after the first proton has dissociated. So again, you have this resonance within the ion that just helps maintain its negative charge. Whereas on H2SO3, after that first proton has dissociated, you really don't see that much resonance. And so we can move on to the last section, 8.11, solubility and pH. Now, again, this is kind of like Unit 7's common ion effect with Le Chatelier's principle. So, basically, if you have a pH dependent ion, like fluoride or, say, chlorite, you will, the more hydrogen that is added, the more it will protonate into its acidic form, and the more that your salt will dissolve. So, say we have calcium fluoride, which dissociates into Ca2 plus and 2F minus. So, this is pretty insoluble. So what we can do to increase solubility is increase the p is no, not increase the pH, decrease the pH, because F minus also has this equilibrium with hydronium to form hydrofluoric acid and H2O, which means that we are decreasing F minus out of solution. Therefore, we induce Le Chatelier's effect because we have a stress on the system of CaF2, and we shift the equilibrium towards the right because we have less fluoride. Now we have come to the end of the review. Like always, ace your exam, have fun.